Chapter 19c, Nucleophilic addition reactions of ketones aldehydes, weak nucleophiles. In the last section, we discussed nucleophilic addition reaction of ketones aldehydes by strong negative charged nucleophiles. And this includes hydride reduction to form alcohols, Grignard reaction to form alcohols, cyanide reaction to form cyanohydrin, and Wittig reaction to convert CO double bond to CC double bond. In this section, we're going to study the nucleophilic addition reaction with weak neutral nucleophiles, and this includes acid-catalyzed hydration to form 1,1-diol, acid-catalyzed alcohol reaction to form acetals, acid-catalyzed amine reaction to form imine-enamine, and Wolff-Kishnin reaction to convert CO double bond to an alkane. Here's a comparison of the mechanisms with strong nucleophile and weak nucleophiles. With strong nucleophiles, the reactions are simple. Reaction undergo two-step mechanism, nucleophilic addition followed by protonation. With weak nucleophiles, the reactions are more complicated. The reaction undergo many more steps, and they are acid catalyzed. The first step, ketones aldehydes are usually protonated by the acid, and the protonated ketone aldehyde then undergo nucleophilic addition, followed by more protonation and then deprotonation, and sometimes intermediate reorganization, and many more steps depends on the reaction. When an aldehyde or ketone is treated with an alcohol, one of the alcohol molecules will attack carbonyl carbon, forms an intermediate called hemiacetal, where a carbon is connected to a hydroxy and a ethoxide. Eventually, another alcohol molecule will attack the same carbon, replace hydroxy to form acetal, where a same carbon connected to ethoxide. Let's draw the mechanism of the first part of the reaction, the hemiacetal formation. So grab a pen and a paper and let's do it together and draw a ketone molecule. And in the solution, the nucleophile is an alcohol. And so let's draw an alcohol, see what happens. So ROH, R means ethyl, methyl, any alkyl group. Oxygen has a lone pair electron, can serve as a nucleophile. But this is a neutral molecule, so it's a weak nucleophile. So it's so weak, it cannot attack this carbonyl carbon. So this does not happen. Instead, the first step for this reaction is the carbonyl carbon is protonated by an acid. So draw an acid molecule, HCl. Or you can draw a hydrogen ion. So HOH, H positive. So either way, show a acid molecule and draw arrow. Okay, one lone pair electron goes to hydrogen to form oxygen-hydrogen bond, so that oxygen is protonated, and the other arrow show hydrogen-chlorine bond break. Two electrons go to the chlorine, forms a chloride ion. Okay, another way, alternatively, you draw lone pair electron goes to the proton, and this electron goes to oxygen. So that will give you a water molecule. So oxygen is also protonated. So here is the product from the first step. All right, this is oxygen ion. The oxygen now has 3 bonds, a double bond, a single bond with hydrogen. So oxygen is protonated, 3 bond lone pair electron, and therefore this oxygen is positive. Okay, remember oxygen carbon, this bond is polar. Oxygen has high electron negativity, it pulls electron away from carbon. And because the oxygen in this ion is a positive charge, it pulls more electron from this carbonyl carbon, and therefore this carbonyl carbon becomes even more positive, and therefore we can say the carbonyl carbon is activated, it becomes more reactive. All right, so the next step now is the nucleophilic attack from alcohol. Okay, so draw alcohol molecule. All right, lone pair electron. An arrow show oxygen carbon forms a bond, and because carbon only can form 4 bonds, so another arrow. Okay, draw another arrow to show the pi bond break. So go this way, pi bond break, 2 electron goes to the oxygen. Okay, so here is the product. All right, so the oxygen now has 2 lone pair electrons due to the pi bond that goes to the oxygen, and the oxygen now has 2 bonds, and therefore 2 bonds, 2 lone pair electron is a neutral oxygen atom. On the other hand, this oxygen coming from this alcohol now has 3 bonds. Okay, one is oxygen carbon bond, one is oxygen hydrogen bond, and this is a new bond between oxygen and the carbon bond. So 3 bonds lone pair electron is a positive charged oxygen. Positive charged oxygen is not stable. It needs to neutralize oxygen. So one way is deprotonate this hydrogen. And in the solution, we have a lot of alcohol molecules. Alcohol molecule is a base, has lone pair electron. So draw an arrow to show oxygen deprotonated hydrogen forms oxygen-hydrogen bond. At the same time, draw another arrow to show oxygen-hydrogen bond break. 2 electrons go to oxygen. So finally, you form hemiacetal. So in this molecule, the carbon, which was the carbonyl carbon, now have a hydroxy. All right, hydroxy oxygen comes from carbonyl oxygen, and a coxide. A coxide comes from alcohol. Okay, hemi means half, so half acetal because we only add 1 coxide. Acetal later we'll see we add 2 coxide to the carbon. All right, and also notice that this reaction has three steps. Protonation is the first step, okay, because the nucleophile is too weak. So protonation to make a ketone or aldehyde more reactive activated to make carbonyl carbon more positive. So that's the protonation step. And then deprotonation step to deprotonate this hydrogen. So the hydrogen or acid is protonated, consumed in the first step. But in the second step, the the third step, the hydrogen is deprotonated. So in other words, it's regenerated. All right, and that's why acid serves as a catalyst. Overall, it's not consumed. First step, it is consumed, but the third step is regenerated. Okay, and so protonation, deprotonation accompany each other, and what you add is a coxide. Okay, a coxide here instead of the whole alcohol, because this proton is deprotonated in the third step. After hemiacetal is formed, the next part of the reaction is to convert hemiacetal into acetal. In other words, we need to add another alkoxide onto this carbon to replace hydroxy group. But hydroxy group is a very poor leaving group. So we learned that hydroxy can be converted into a better leaving group by protonation. And remember, it's in acidic condition. So we draw an acid molecule to show the oxygen is protonated. So here is protonated hemiacetal, where the oxygen has 3 bonds with a lone pair electron and a positive charge. Now, if we let these water molecules simply to leave, then this carbon will have 3 bonds, and that's not good. Instead, we draw 2 arrows to show that the oxygen carbon forms a double bond, and the leaving group leave, so that the carbon has 3 or 4 bonds. Okay. Now, this is the product from the second step, and it's rotated version of this one. So if you rotate, the double bond carbon-oxygen bond becomes vertical, and this alkyl group 1, 2 is here. Okay, so that's the product from the second step. Oxygen has 3 bonds, positive charge here. So positive charge oxygen is not stable. But this cannot lose a hydrogen because it doesn't have hydrogen like the formation of hemiacetal. So we cannot lose hydrogen. Instead, we know this bond is polar and this carbon is positive charged. So the next step, alcohol nucleophilic addition. Now this is the second attack, and this is the step to add another alkoxide. So draw two arrows. One is lone pair electron from oxygen attack carbon, forms oxygen carbon bond, and the other pi bond break goes to the oxygen. Okay, and that'll give you a intermediate that has a alkoxide there, but this is another alcohol, but the oxygen is a positive charge with hydrogen. Again, this oxygen is not stable, so we need to remove the charge, and one way to do is deprotonation. So remember, we have lots of alcohol serve as a base, so deprotonate this hydrogen by drawing two arrows, one to form oxygen hydrogen bond, the other the old bond break give oxygen, that forms a neutral molecule acetal. Okay, so in this acetal, carbon have two alkoxide, all right, in this. So the reaction here involves 4 steps. The first step is the hemiacetal protonation, all right, to make hydroxy a better leaving group, and then a reform to CO double bond. So here reform a CO double bond, at the same time leaving group leave. And then the third step is the nucleophilic attack. All right, so that's the step to add the second alkoxide. Okay, but when you add the whole molecule alcohol, the proton needs to be deprotonated, and that's the last step to give you acetal. Let's go over the whole mechanism. Since neutral nucleophiles are too weak to attack, ketones aldehydes need to be protonated first. So first step, protonation of ketone aldehyde to form protonated ketone aldehyde. Carbonyl carbon becomes activated. So second step, nucleophilic addition. All right, and then followed by deprotonation of the hydrogen, give you hemiacetal. In this molecule, one alkoxide is added. Hydroxy group is too weak, too bad leaving group, so it is need to be protonated, forms a better leaving group. Okay, and then molecules reform to form CO double bond and the leaving group leave. Okay, and this intermediate oxygen has a positive charge. It's under second attack, nucleophilic addition. All right, followed by deprotonation, give you the final product, acetal. The reaction involves 7 steps. 4 steps are proton transfer steps, and the first step is the protonation, and then here deprotonation, protonation, deprotonation. Okay, that's 4 steps. And then 2 nucleophilic addition. Here 1 nucleophilic addition, here second nucleophilic addition. These 2 are the key steps to add alkoxide onto the carbonyl carbon. And 1 step is reform CO double bond. Here shows the overall reaction of acetal formation. So in this overall reaction, 1 mole of ketone aldehyde react with 2 moles alcohol, forms 1 mole of acetal and 2 moles of water using acid as a catalyst. Note that the reaction is reversible. That means the product also go back to the reactants. So if you let the reaction proceed, only small amount of the ketone aldehyde will be converted to the acetal because there's an equilibrium. So how do we drive the reaction go forward to make more product? Now in Jenkin, you learned that the Shetler principle says that if you add product, the reaction go reverse. If you remove the product, the reaction will go forward. So in other words, if you remove water, which is one of the product, the reaction will go forward to produce more acetal. On the other hand, if you add water, which is one of the product, the reaction go reverse. In other words, the acetal will go back to the ketone aldehyde. In laboratory, chemists use a dim stock distillation trap. In this setup, the mixture is heated in this round bottom flask. Some of the mixture will be vaporized, and so vaporized go up and be condensed in this condenser, becomes liquid, and here is the trap. So in this trap, the liquid separate into two layers. On the bottom is the water layer. So here is the water layer that is produced in the reaction, and the organic layer, which includes the reactants and some product, is on the top of this trap. Okay, this organic layer can go back to the mixture in the round bottom flask, and the water can be released by this valve. So during the reaction, we can continuously remove water. So water is the product. When you remove water, this will drive the reaction go forward and maximize the yield of the acetal formation. On the other hand, if you add water, okay, the acetal will go back to the ketone aldehyde, and that suggests that we can use the formation of acetal as a protection method for the ketone aldehyde. Just like alcohols can be protected by forming OTMS. Remember? All right. Here we can protect ketone aldehyde by forming acetal. And then in the end, we can remove the acetal by adding water. So it goes back to the ketone aldehyde. Here we show an acetal molecule on the left side. And we can recognize an acetal molecule by locating a carbon that is connected to two alkoxy groups. This acetal can be synthesized by mixing a corresponding ketone with 2 moles of alcohol and acid as a catalyst. And that gives you an acetal molecule. Now on the right side, this is also an acetal because this carbon is connected to a alkoxy group. But in this case, these alkyl groups are connected, and this forms a cycle, and so it's called a cyclic acetal. Cyclic acetal can be synthesized by the corresponding ketone with 1 mole of diol and acid catalyst. Now with a diol, the one of the hydroxy group, okay, attack carbonyl carbon first, followed by deprotonation, rearrangement, and then the other hydroxy group attack the second time, and that will give you this cyclic acetal. Cyclic acetal is more efficient and more commonly used for protection of ketones and aldehydes. Here is an example. We have a molecule with 2 functional groups, a ketone and an ester. And we want to convert this ester functional group to alcohol, but keep ketone untouched. So we know, you should remember that to convert ester into alcohol, we should use a reducing reagent for the reduction reaction. So reducing reagent should use lithium aluminum hydride. But this reducing reagent also reduces ketone. And therefore, we have to protect the ketone before the reduction of ester. So first step, we add ethylene glycol, okay, here, which is a diol with 2 carbon, and that will also under acidic condition, and then give you a cyclic acetal. Okay, note that you also have 2 carbon here because ethylene glycol has 2 carbons. Now after ketone is protected, now add the lithium aluminum hydride followed by protonation, acid protonation, and that give you alcohol. Okay, and then deprotection by acid water solution, and this acetyl go back to ketone. That give you the final product. Practice. Show the structure of acetyl you would obtain by acid catalyzed reaction of this 2-pentanone, which is a ketone, and 1,3-propane-diol. Okay, so this is a diol with 3 carbon in acidic condition. Okay, so what's the product? Well, first let's draw the diol. So 3 carbon with 2 hydroxy group. Okay, so during the reaction, one step involves this hydroxy attack carbonyl carbon, and the other step is the second attack from this hydroxy. Okay, during one of the process, oxygen forms water leave, and so the product should be this one. All right, this is the acetyl, cyclic acetyl. Note that here I'm not trying to draw the detailed mechanism. The mechanism involves 7 steps. So first oxygen protonate, and then attack, and then deprotonate, rearrangement, and then second attack. So there's many steps. Here I'm just show the idea what's going on to make the product. Acetyls, hemiacetyls are also commonly found in biomolecules. For example, in open chain glucose, a hydroxy may attack an aldehyde functional group to form a cyclic hemiacetyl glucose, and this carbon connect to hydroxy and a alkoxide, and that's a hemiacetyl. Lactose contains hemiacetyl and acetyls. Aldehydes and ketones also react with water to form 1,1-diol. 2 hydroxy groups attached to the same carbon, which is also called germinal diols. The reaction usually favors the reverse reaction. In other words, most ketones aldehydes, they do not go to the product in significant amount. This is due to the steric effect. In the product, the alkyl groups are crowded, making the product unstable. The reaction may favor the product if the reactant has a small size. One example is the formaldehyde. The reaction has 99.9% conversion to the diol, 1,1-diol. The mechanism of this hydration reaction in acidic condition is similar to the mechanism to form hemiacetyl, and I hope you're already good at drawing the mechanism of formation of hemiacetyl, and now it's fun to draw this mechanism. So as usual, ketone aldehydes need to be protonated in acidic condition. So draw the protonation, all right? And the protonated ketone or aldehyde now is under attack by a weak nucleophile. In this case, is water. So draw arrows to show the nucleophilic addition to this protonated ketone or aldehyde. Okay, in the product, oxygen, the added water. Okay, oxygen is a positive charge with 3 bonds. All right, so one of the hydrogen now is deprotonated by another water molecule, and that gives you 1,1-diol. The hydration reaction can also be catalyzed by base, and the mechanism is simpler. In basic condition, the hydroxide, which is a strong base and also a strong nucleophile, can attack carbonyl carbon directly to form an alkoxide with a hydroxy group. The alkoxide then protonated by a water molecule give you the 1,1-diol or hydrate. So far, we have studied the reactions of ketones aldehydes with alcohols and water. The reactions follow the same mechanism. First, the carbonyl group is protonated, and then nucleophile attack carbonyl carbon followed by protonation give you this product, as in hemiacetyl and 1,1-diol. The hydroxy group may be protonated again, and then the nucleophile attack the second time followed by protonation give you this product, as in acetyl. Suppose the nucleophile is amine. This is amine. Will the reaction follow the same procedure? give you the similar products. Not exactly. It turns out that the product depends on what type of amine. If it's a primary amine, the product is called imine. You have a CN double bond. If the amine is secondary, then the product is called enamine. You have a CC double bond with a nitrogen attached to this carbon. The best way to understand the organic reaction or predict the product is draw the reaction mechanism. So let's draw the mechanism of imine formation. And here I also show the hemiacetal formation mechanism for comparison. And just like hemiacetal formation, the first step, ketone aldehyde needs to be protonated. All right, so draw an acid, okay? Now we can also draw HCl, just like here, which is equivalent. Just show a acid molecule, and lone pair electron oxygen go to the proton, and here it forms water. So ketone aldehyde is protonated. So these steps are the same. Okay. The next, protonated ketone aldehyde is under attack by a amine. So here amine. We use a primary amine as an example. So primary amine means nitrogen is connected to one carbon. So R is a alkyl group, one alkyl group with two hydrogen, because nitrogen have 3 bonds. So 2 hydrogen with one alkyl group and the lone pair electron, and that's the primary amine. The primary amine lone pair electron attack carbon to form nitrogen-carbon bond. Pi bond between carbon-oxygen break goes to oxygen, and that forms this molecule. So up to this point, they are same. All right, and again, the nitrogen now has an extra bonds. So 4 bonds with a positive charge. In order to stabilize the molecule, it deprotonates to neutralize the nitrogen atom. So deprotonation by water here, and so that will give you a molecule called a carbonyl amine. So in this molecule, this carbon comes from carbonyl carbon that connect to hydroxy with an amino group, just like hemiacetal, which carbon is connected to hydroxy with a alkoxide. Hemiacetal is an intermediate towards acetal. Similarly, carbonyl amine is an intermediate towards the final product of imine. Okay, so up to this carbonyl amine, the mechanism is the same as the formation of hemiacetal. After carbonyl amine is formed, the next step is to protonate this hydroxy group, just like hemiacetal, where the hydroxy group is protonated to form a beta leaving group water. Water leave, which is assisted by oxygen to form CO double bond. Similarly, carbonyl amine is protonated, forms a beta leaving group water, and water leave, which is assisted by nitrogen to form CN double bond. So the two mechanisms are very similar up to this point. The only difference is one is oxygen, one is nitrogen. Okay, the real difference of these two mechanisms starts from here. Okay, in the case of alcohol reaction, the oxygen has a positive charge. The molecule is not stable, which can be stabilized by the second attack. Okay, second alcohol attack followed by deprotonation give you a neutral molecule acetal, where you have 2 alkoxide. On the other hand, in the case of amine reaction, the nitrogen has a positive charge, but also have a hydrogen. Okay, remember we start with a primary amine, so R, 1 alkyl group with nitrogen, 2 hydrogen with a lone pair electron. This is the primary amine. So primary amine has 2 hydrogen. One of the hydrogen was already deprotonated before carbonyl amine was formed. All right, so remember you have 2 hydrogen, but this is deprotonated. So now you still have 1 hydrogen. by deprotonating this hydrogen, the positive charge can be removed, and that gives you a neutral molecule called imine. And in imine, you have a CN double bond. All right. So the two mechanisms are almost the same up to this point. All right. And the difference is in amine reaction, the intermediate has a nitrogen positive charge with a proton. When proton is deprotonated, you get a neutral molecule imine. But in alcohol reaction, the intermediate here does not have hydrogen. Okay, so you cannot lose hydrogen. You certainly cannot use a alkyl group, and therefore a second attack, alcohol attack, followed by deprotonation, give you acetal. Okay, so I suggest you practice the mechanism and see if you can draw the mechanism and how imine is formed when primary amine is as a reactant. We just showed the mechanism of a reaction between a ketone or aldehyde with a primary amine. The product is imine, where you have a CN double bond. What if the nucleophile is a secondary amine? Now, secondary amine is a nitrogen with two alkyl groups, with one hydrogen and a lone pair electron. Okay, that's a secondary amine. It turns out that the mechanisms are almost the same except the last step. So let's go over this process. So again, primary amine is a neutral molecule which is not strong enough to attack carbonyl carbon to form a stable compound. Instead, the carbonyl group needs to be protonated, just like the case of primary amine. So a protonation give you protonated carbonyl, which now is under attack by secondary amine. All right. So now you have a carbon hydroxy group. All right. You also have a nitrogen attached with a positive charge with one hydrogen, and this hydrogen can be deprotonated. Okay, forms a carbonyl amine. Note that here is a carbonyl amine from secondary amine, and here is a carbonyl amine from primary amine. All right, they are very similar up to this point. So next, hydroxy needs to be protonated to form a beta leaving group. So again, it's protonation, give you a beta leaving group, and the leaving group leave, which is assisted by nitrogen. So that forms imine ion. So again, up to this point, almost the same as in the case of primary amine, also forms imine ion. But in the case of primary amine, the imine ion nitrogen has a hydrogen, okay? Because primary amine has two hydrogens. It deprotonates at this point, and there's still one hydrogen here. And so all you need to do is deprotonate this hydrogen, molecule becomes neutral imine with a CN double bond. But in the case of secondary amine, the amine only have one hydrogen. After it deprotonate at this step, then there's no hydrogen in the imine ion. The nitrogen positive charge connect to two alkyl group. There's no hydrogen to be deprotonated. Instead, there's another path to stabilize the product, and that is it can deprotonate a hydrogen 2 atoms away from the nitrogen. Okay, so by deprotonating this hydrogen, the 2 electrons between this carbon-hydrogen bond goes to carbon-carbon bond to form a double bond here. And then the pi bond between CN break goes to nitrogen to neutralize the nitrogen. So now you have a double bond here, all right, neighboring to the nitrogen. And the nitrogen has a lone pair electron that comes from the pi bond. And that's a neutral molecule called enamine. Okay, so you can see two mechanisms are almost the same up to this point. The imine ion. In the case of primary amine, imine ion still has one hydrogen. It can be deprotonated, forms imine with a CN double bond. In the case of secondary amine, the imine ion has no hydrogen to be deprotonated, so a hydrogen from an atom 2 atoms away can be deprotonated, give you a CC double bond, and with a amine attached to it, and that's called enamine. Okay. We just showed that when a ketone or aldehyde react with a primary amine, where nitrogen has 2 hydrogens, both can be deprotonated. The product is a CN double bond, which is an imine. When the ketone aldehyde react with secondary amine, where nitrogen only have 1 hydrogen, then the iminium ion has no hydrogen, so the hydrogen 2 atoms away needs to be deprotonated, give you a double bond carbon-carbon double bond, and the amine attached to it, and that's called enamine. Okay, because both reactions are catalyzed by acid, so the pH value has an important effect on the reaction rate. If the pH value is too high, then the solution becomes too basic. There's no acid to catalyze reaction. Reaction must be slow. If the pH is too low, then the solution becomes too acidic, then amines will be protonated. Remember, amines are bases. They will be protonated. And when amines are protonated, they cannot participate in the reaction. The best pH value is around 4.5, and that will give you the maximum reaction rate. Let's predict the product of a reaction between a ketone and an amine. So first, let's identify what amines do we have. This is a primary amine because nitrogen connects to 1 carbon with 2 hydrogens. That's a primary amine. For primary amine, nitrogen will replace oxygen. 2 hydrogens will be deprotonated, forms a CN double bond. And so note that we have a CN double bond with the methyl group come from here, primary amine. All right, so this is an imine. Okay, next one, this is a secondary amine. Nitrogen connect to 2 carbon with 1 hydrogen. So again, for secondary amine, nitrogen will replace oxygen, but in this case, a hydrogen 2 atoms away from nitrogen will be deprotonated. This forms a double bond here, and this is a nitrogen. So the product is a CC double bond with a nitrogen connected to the carbon, and the 2 methyl groups come from this secondary amine, and this is an enamine. Primary amines can react with the ketones to form imines. Imines are usually stable solid with a specific melting point, can be easily characterized, and this allows us to characterize unknown amines. For example, this is an amine, and suppose we are not sure if we have this or not. We will let this compound to react with acetone to form imine. And by characterizing this imine, then we can tell if we have this amine or not. This molecule is called hydrazine. Hydrazine contains 2 nitrogens. Each nitrogen has 2 hydrogens, and therefore hydrazine is also a primary amine. When ketones aldehyde is treated with hydrazine followed by strong base potassium hydroxide, CO double bond is reduced to 2CH bond, carbon-hydrogen bond, and this is called Wolff-Kishner reaction. Wolff-Kishner reaction is a useful and general method for converting aldehyde or ketone into an alkane. Here shows the mechanism of Wolff-Kishner reaction, and this is the hydrazine, which is a primary amine. If we focus on 1 nitrogen and imagine the molecule is H2N with an R group, and that's a regular primary amine with 1 alkyl group, 2 hydrogen. All right. When primary amine react with a ketone, the product should be an imine with nitrogen with a R group, and the 2 hydrogens are both deprotonated. So that should be the product. Because this R group in hydrogen is another nitrogen, and therefore this is the product when hydrogen is used. So you have a second nitrogen with still two hydrogens. Okay. Now, if the solution contains a strong base, okay, when strong base is added, the hydroxy group will deprotonate one of these hydrogen to form an anion nitrogen. So you have two pairs of electrons with a negative charge. Lone pair electron come back between nitrogen forms a double bond here, and the pi bond goes to carbon, forms a carbanion. This carbanion can be protonated by water. All right. So now you have one hydrogen added to the carbon, and the nitrogen forms a double bond here. But the second nitrogen still have one more hydrogen, and this hydrogen can be deprotonated again by a strong base. And these two electrons go to nitrogen forms a triple bond. So this comes here, forms a triple bond, and the bond between carbon nitrogen break, give a carbanion again, and this protonate forms another carbon hydrogen bond. And so that gives you alkane. At the same time, a nitrogen is formed. Because nitrogen gas has 3 bonds, triple bond, nitrogen is a very stable molecule, and therefore formation of this nitrogen molecule is the driving force for the whole reaction to proceed to completion. Okay, so you can see here the ketone aldehyde reaction with hydrazine convert a CO double bond to 2 CH bond, a reduction reaction. It's an alkane, and if the solution does not have base, then the reaction stops here. This is just the regular primary amine react with ketone, form a imine. But whenever base is added, the two hydrogens on the second nitrogen will be deprotonated, and a triple bond between two nitrogens is formed. A nitrogen gas is formed, and then two hydrogens are added to the carbon to form an alkane. Here shows 2 examples. In the first case, we have a ketone with a CO double bond, which is treated by hydrazine and a strong base. And as we know, the combination of hydrazine and the base will convert the CO double bond into 2 CH-CH bond, and that's an alkane. Okay. Of course, this also generates nitrogen gas and water. In the second case, we have an aldehyde, also with a CO double bond, and which is treated by hydrazine with a strong base, and that will convert this CO double bond into 2 CH-CH bond. Again, it's an alkane with nitrogen gas and water. In summary, when ketones or aldehydes are treated by neutral nucleophiles, the reaction mechanisms have many more steps than the negative charged nucleophiles. The reactions requires acid as a catalyst. The first step always protonate the ketone or aldehyde. So the first step, aldehyde ketone is protonated. The protonated ketone aldehyde then undergo nucleophilic addition, followed by deprotonation. All right, give you intermediate, and the intermediate may undergo more protonation, deprotonation, or second nucleophilic addition. All right, more steps depends on the reactants. So when ketones aldehydes react with water under acidic condition, the product is 1,1-diol or CHEM diol. When ketones aldehydes react with alcohols under acidic condition, the first it forms a hemiacetal, where one alkoxide added to the carbonyl carbon, and the carbonyl group becomes hydroxy group. Eventually, a second alcohol adds to the carbonyl carbon. The hydroxy becomes a leaving group, and the final product is acetal, 2 alkoxide added to the carbonyl carbon. And when the ketone aldehyde is treated with a primary amine, okay, primary amine where you have 2 hydrogens, the final product is a imine where you have a CN double bond. 2 hydrogens are both deprotonated. Okay, when ketones aldehydes are treated with a secondary amine where you have 2 alkyl groups, only 1 hydrogen, the final product is a enamine where you have a CC double bond attached to the nitrogen of the amine. Okay, when the amine is hydrazine and combined with a strong base, the final product is an alkane. So ketone aldehyde CO double bond is reduced to alkane. Here shows the homework problems for this section.